Hello class, here we are continuing on the journey through pulmonary physiology, and we're going to talk about gas transport. Here are our learning objectives. What in the heck are partial pressures and how do we calculate them? How do we talk about diffusion flux and diffusion capacity, and what kind of things influence diffusion flux and capacity? We want to distinguish between a diffusion limited and a perfusion limited gas. We want to figure out what O2 is in a healthy person and what's going on when O2 is diffusion limited. We want to talk about how oxygen's carried in the blood, the oxyhemoglobin saturation curve, and we want to talk about saturation versus content. We want to talk about the Bohr Effect, what causes right and left shifts of the oxyhemoglobin curve, what's going on with carbon monoxide poisoning, how CO2 is carried in the blood, and the CO2 dissociation curve versus the oxyhemoglobin curve, and we're going to finish up with the Haldane effect. So partial pressure is kind of like a concentration. If you know the percent of the air that's due to a particular gas and you multiply times the atmospheric pressure, you calculate the partial pressure. We care about partial pressures because they tell us about diffusion gradients and diffusion directions. Partial pressure determines how much of a gas dissolves in the plasma, and it also tells us about saturation with hemoglobin, which we'll get to in a little bit. All right, so here's the diffusion flux equation. So the flux is, so the flux is related to area. So the greater the area, the more diffusion flux, divided by the thickness or the distance. So the farther you have to go, the lower the diffusion flux. The solubility of the gas and the size of the gas. So bigger gases diffuse slower, more soluble gases diffuse faster. And then we have our pressure gradient. So when we think about this solubility times molecular weight, that is the characteristics of the gas, and we can talk about something called a diffusion capacity. That's the volume of gas crossing a diffusion membrane per minute for each millimeter of mercury at partial pressure. So that says something about how well a particular gas diffuses. Engineering types may be more familiar with J is the flux, is some constant D, which gets us the solubility and the molecular weight of the gas, times the change in concentration, P1 minus P2, divided by the change in distance, so delta C divided by delta T. What's important to understand about this particular permutation of the equation is that diffusion slows over distance. That's because when you first start diffusing, you have a big concentration gradient, and then as molecules make their way along, the diffusion front has a smaller concentration gradient. And so diffusion goes slower and slower and slower. So diffusion is great for short distances. If you want to go through a cell membrane or across a cell, it's great. If you want to diffuse long distances, it's terrible. So for fun, once I calculated how long it would take an oxygen molecule to diffuse from my lung down to my big toe, and it turns out it's about 17,000 hours. But if you want to know how oxygen is going to diffuse across a little cell, it's a fraction of a second. So it's a beautiful process for short distances. And remember that the lungs are adapted to maximize diffusion flux. So we have very vast surface area. We have short diffusion distances. Our gases are oxygen and CO2, and we have nice stable gradients in the lungs. And here we are with this equation. So remember, we start out with oxygen in the air, very little CO2 in the air. This comes into the lungs. Immediately the partial pressure of oxygen drops because we add water vapor, and then that gas mixes in the alveoli. And so now here we have a PO2 of about 105, a PCO2 of about 40. When this exchanges with the venous blood, we've got a PO2 of 100, a PCO2 of 40. Notice the 5 millimeter of mercury difference. That difference occurs because of inequities in ventilation and perfusion relationships, and we'll talk about that in the next video lecture. We won't talk about that yet. But we have our partial pressures in the blood. These gases are then carried down to the cells. There's an exchange at the tissue capillaries, and so much lower than 100 millimeters of mercury, much lower than 40 in the cells. Remember, we have to have greater than 5, greater than 3 actually to have oxidative phosphorylation. And this is the place where CO2 is being produced, so of course it's higher than what's in the venous blood. And then this comes to load up once again. So, transport limitations. A diffusion limited gas means it's the diffusion gradient that's preventing more gas from diffusing. You have plenty of blood. The problem is the diffusion gradient promoting diffusion. And the way to increase diffusion is to increase the diffusion gradient. All right, perfusion limited. That means diffusion happens very quickly, and what limits the transport of the gas is having new blood to bring the gas to. So the question is, what is oxygen? So here's an interesting little graph. Here we are along the length of a capillary, and here we have pulmonary capillary PO2. So we have venous blood coming into a pulmonary capillary, and the PO2 is about 40. Notice gas is diffusing into the venous blood and turning it into arterial blood, and now we have the capillary blood having the same PO2 as the alveoli, and we're about a third of the way through the capillary. So we can't get many more oxygen in here. To get more oxygen loaded into the body, we have to bring in more blood. So in a healthy person, oxygen is a perfusion-limited gas. Another example of a perfusion-limited gas is nitrous oxide. It just whizzes right into the blood. So it's the mother of perfusion-limited gases. Now, in a diseased lung, diffusion is being impaired, maybe because of scarring or an increased thickness or a loss of alveoli. And so in the disease state, oxygen becomes a diffusion-limited gas. Well, how could we help this person? If oxygen has become diffusion-limited, well, we would put this person on oxygen. We could give them oxygen, increase the concentration gradient, and promote better diffusion. What's an example of something that's normally a diffusion-limited gas? And the answer is carbon monoxide. If you want to test what the diffusion characteristics of the lung are, you use carbon monoxide. You have to be very careful and use very teeny tiny concentrations of it, but that's an example of a typically diffusion-limited gas. So oxygen is inspired, brought into the alveoli. There's a concentration gradient, a partial pressure gradient for oxygen to diffuse across the barrier, the epithelium of the alveolus and the endothelium of the capillary, and then it has to dissolve in the blood. And the partial pressure of oxygen determines how much dissolves. There's something called Henry's law. The bigger the partial pressure of a gas, the more the gas dissolves in a liquid. So O2 has to dissolve in the blood, so then it starts to exert PO2 in the blood. Then O2 can diffuse into the cell, find hemoglobin and bind. And now it's no longer oxygen, it's oxyhemoglobin. So now we have another, we have the ability for another O2 to diffuse in and take its place. So oxygen comes in, and then when it binds to hemoglobin, it no longer exerts PO2. So another oxygen can come in. So we fully load up hemoglobin. Oxygen then diffuses until the partial pressure gradient is gone, and then we need for that blood to move along so we can have new blood to load up with oxygen. At the tissues, the cells are using the oxygen, so there's a low PO2 out here. That low PO2 encourages oxygen to diffuse out of the capillary. That encourages oxygen to unbind from hemoglobin, so we continue to have a supply of oxygen to diffuse into the cells. So this implies that there are two types of way that oxygen is carried in the blood. It's carried in the dissolved form, and it's the dissolved form that exerts PO2. But the bulk of oxygen is carried bound to hemoglobin in the bound form. So we have dissolved and bound, and the bound hemoglobin is more important. Something got cut off here. About 97% of the oxygen running around in the blood is bound to hemoglobin. A very small portion is dissolved in the blood, but we have to have the dissolved because the dissolved is what exerts PO2, and the PO2 is what tells it where to diffuse and how to bind to hemoglobin. So here's a liquid with some oxygen in it, and we have two equal proportions. Then we add some hemoglobin molecules on one side. So an oxygen molecule binds, another one binds, and that lowers the PO2. So an O2 molecule is going to come over, and it's going to bind, no longer exert PO2, that lowers the PO2. Another one's going to come in and bind, that lowers the PO2. But once our two hemoglobin molecules are bound up with oxygen, and the PO2 is equal, then no more diffusion occurs. So I'm getting across this idea that you have oxygen dissolved in the blood, then it hitches a ride on hemoglobin, and then that leaves a space for another O2 who can diffuse in. So here's the oxygen saturation curve. I hope you've all seen this at least once before. So on our x-axis is PO2, on our y-axis is hemoglobin saturation. That's a percentage. It's the percentage of binding sites that are occupied with oxygen. Here's systemic blood, arterial blood. We're about 100% saturated. In a real walk and talk in person, it's probably 98% saturated, but we'll round it off to 100 for now. And as we are, as the PO2 is dropping to 60, etc., we're still pretty highly saturated. Down in the venous system, where PO2 is 40, we're still 75% saturated. So at higher PO2s, hemoglobin is a binding molecule. But around 60, going into 40, it turns into a releasing molecule. And as you can see, from, say, 40 to 20, there's a massive amount of releasing that occurs. And we see as that happens, then our red molecule turns into a blue molecule. So you are going to have to learn how to calculate oxygen content, and it's going to be fun. So here we have a person who has 15 grams of hemoglobin in 100 mils of blood. That's called a grams percent. And their PO2 is 100, and I'm going to say they're 100% saturated. So we have to calculate what's the bound content, what's the dissolved content. How do I do that? Well, for every gram of hemoglobin, we bind 1.34 mils of O2 per gram per 100 mils of blood. That way I don't have to deal with blood volume. So 15 times 1.34 equals 20.1 vols per cent. I could have a times a 1 because we're 100% saturated. That's the bound content. Then I add my dissolved content, and I know that for every millimeter of mercury, 0.003 mils of O2 dissolve. So 0.003 times 100 is 0.3. That's the bound content, that's the dissolved content, that's the total content. If I take the same person and they're in the venous blood at 40 millimeters of mercury, I'm 75% saturated. So 15 times 1.34 times 0.75. The bound content has gone down to 15 vols per cent. At 40 millimeters of mercury, 0.003 O2 per 100 mils per, I don't have my per millimeter mercury. That's 0.2 vols per cent. That's the bound content, that's the dissolved content, that's the total content. So that's arterial blood. Whoops. That's venous blood. So I can do something called an oxygen extraction. So 20 minus 15 vols per cent divided by 20 vols per cent means I've extracted about 25% of the O2. That's a typical figure for all over the body. A tissue that's working harder might extract more. Remember, your coronaries extract a lot of oxygen. 75, 80% of the oxygen. That's why you have to deliver more blood to the coronaries. You can't just extract more. Alrighty? Now, what if we had a person with less hemoglobin? Here we have a person with 10 grams of hemoglobin per 100 mils of blood. At a PO2 of 100, they're 100% saturated. So 10 grams times 1.34 times 1, because they're 100% saturated. 13 vols per cent is the bound. 0.3 vols per cent is the dissolved. That's a total of 13.7 vols per cent. Now, am I ready for this? I'm not. So think about person 1. Do you see 0.3 vols per cent? Person 1 and person 3 have the same dissolved content. But person 1 has a greater total content because they have a greater bound content, because they have a more, they have a higher carrying capacity. But if they both have a PO2 of 100, see that? They both have a PO2 of 100, they're both 100% saturated. It's very important that you understand that. If all you have is saturation, if all you have is a little pulse oximeter on somebody's finger telling you they're 98% saturated, and you don't know what that person's hemoglobin is, you don't know how much oxygen they have. And the reason why it's important to realize that is that people with anemia look better than they actually are. If somebody's got anemia, they're supposed to have 15 grams per cent, but they have 7 grams per cent. They have half the hemoglobin they're supposed to have. You put that little pulse oximeter on it, it's going to say 98%. But they're too tired to hardly walk down the street. Why is that? Because they're anemic. It's very important. And we'll talk about this more in class, but this is really something I want you to get, the difference between saturation and content. Alrighty. Here's the Bohr effect. It means you can fine-tune the binding of oxygen to hemoglobin. So these yellow curves are all sort of healthy, normal conditions. You can shift the curve to the right meaning promoting release, or you can shift the curve to the left, promoting binding. And what does that? Well, things that increase your metabolism. Increase temperature, increase CO2, increase hydrogen ion, increase glycolysis metabolites, which is what this DPG stuff is. These are all things that say, hey, we're working harder. Shift that curve and give us a little more oxygen. Now, if you're not working as hard, low temperatures, low CO2, a high pH, or a low hydrogen ion concentration, that promotes binding. Those tissues don't need as much oxygen. And so, right shift, right as in release. Left shift, left as in latch. This is a way to fine-tune the behavior of hemoglobin in various tissues that are working more or less. One caveat is the hydrogen ion. People with alkalosis, left shift, and they don't necessarily need a left shift. So that can withhold oxygen from the tissues when the people actually need the oxygen. So somebody with systemic alkalosis, this is actually ends up not being a helpful thing. Otherwise, when you have local areas of differing CO2s or differing pHs that adjust the behavior of hemoglobin to what's going on in that particular tissue, that is called the Bohr effect. Carbon monoxide, CO, is the byproduct of incomplete combustion. And carbon monoxide is a very dangerous molecule because it binds to hemoglobin in the spot that oxygen binds, but with a much higher affinity. So you could have 200 molecules of oxygen and 1 molecule of carbon monoxide, and carbon monoxide would probably hog the binding site. So it decreases the content, it decreases the bound content of oxygen. But if the person is breathing normally, their arterial blood gases, and what I mean by that is their PO2 and their PCO2s, will be normal. And because PCO2 is normal in the early stages, there's no shortness of breath. People don't know what hit them. If a family's furnace is broken and it's putting out carbon monoxide, nobody knows. Everybody thinks that people feel kind of achy, they feel tired, they feel headachy, everybody thinks they've got the flu. No, they don't. Their furnace is killing them. The other problem is that carbon monoxide does not allow oxygen to release, so it kind of causes a left shift. Very, very dangerous, which is why people should have carbon monoxide detectors in their home, because you can't see it and you can't smell it and you don't feel short of breath. Carbon dioxide binds to hemoglobin, but in a different spot than oxygen does. It binds to the amine group. So a little bit binds to hemoglobin, a little bit dissolves, but the bulk of our carbon dioxide combines with water to form bicarbonate. That's the most common form of CO2 in the blood. So here we go. Here's some cells producing carbon dioxide. It dissolves in the tissues, diffuses into the capillary, so some of it is dissolved. It diffuses into the cell, some of it binds to hemoglobin. Now, hemoglobin that is not bound to oxygen is very good at buffering hydrogen ions. So hydrogen ions bind to the hemoglobin and promote the conversion of CO2 and water to carbonic acid and bicarb. Hydrogen goes and hitches a ride on hemoglobin. Bicarb can build up. It shifts out of the cell and chloride shifts in. It's called the chloride shift. And then the opposite thing happens at the lungs. As CO2 is exhaled, we're pulling out dissolved CO2. We're pulling CO2 off of hemoglobin. That little hydrogen can come along and bind to a bicarb. It goes backwards with the help of carbonic anhydrase to make CO2, which we can continue to exhale. Now, the fact that we can turn carbon monoxide into bicarbonate is an interesting thing. Notice here's PCO2, here's CO2 content, and that's all the forms. That's the dissolved, that's the bound, that's the bicarb. Notice that the curve is linear. The oxyhemoglobin curve is sigmoid. It saturates. You get to a point where you can't bind any more hemoglobin with oxygen. But the carbon dioxide curve is linear. Now, if you have lower levels of oxygen, that encourages the conversion of carbon dioxide to bicarbonate. And so, in the arterial blood, we have a certain amount of carbon dioxide, but in the venous blood, as the O2 goes down, we enhance the conversion of CO2 to bicarbonate. Why? Because as lower levels of oxygen in the blood, hemoglobin is better able to bind up hydrogen ions and promote the conversion of CO2 and water into bicarbonate and hydrogen ion. So this is the Haldane effect. So the Bohr effect is shifts in the oxygen relationship in the presence of high CO2. The Haldane effect is the shift in the CO2 relationship in the presence of low O2. So low O2 enhances the loading of carbon dioxide into the blood in the form of bicarbonate. So here, this is in words. Low O2 promotes formation of bicarbonate and CO2 binding to hemoglobin. High O2 promotes formation of CO2 and CO2 release from hemoglobin, so then you can exhale that.